Hello, everyone. Welcome to the Gas Mapping LiDAR Airborne Methane Detection and Emissions Monitoring webinar. My name is Eric Rodriguez. I am the team lead for gas emissions R&D here at SoCalGas. My group investigates technologies to detect, quantify, and reduce methane emissions associated with the natural gas system. And before we get started today, just going to go through a few housekeeping issues. Let me go to the next slide. Sorry, having some technical issues. Okay, so before we begin, I'd like to walk everyone through Co2 webinar. Sorry, my notes are missing. So before we begin, I'd like to go through GoTo webinar. The toolbar should be visible to all attendees on the side. Please enter any questions in the questions box. We'll review these during the Q&A session after the presentation. During the Q&A session, we will also open up the discussion for verbal questions. Please click the raise hand icon to be called on during the Q&A session. When you are called on to ask a question, we will first grant you access to unmute, then you must manually unmute yourself. Please go back on mute after asking your question. Finally, you will find a few valuable documents in the handouts box on the side of the GoTo webinar toolbar. Now, comment on SoCalGas's commitment to diversity. SoCalGas is dedicated to improving the quality of life in the diverse communities we serve. To support this commitment, SoCalGas RD&D staff conduct outreach efforts and activities to engage with disadvantaged and underrepresented groups through California, notify researchers, entrepreneurs, and businesses about RD&D program funding opportunities, share the results from RD&D projects to inform and educate the general public. And today's webinar is just one of those ways that we do this. And we track and report progress in diversity outreach efforts in our annual report. The SoCalGas RD&D program, which stands for Research, Development, and Demonstration, is divided into 5 areas that span the entire energy supply chain. We have low carbon resources, which focuses on renewables, carbon capture, utilization, and sequestration. We have gas operations, which focuses on environmental safety, operations technology, system design and materials, etc. Clean transportation, clean generation, and customer end use applications such as residential and commercial applications, industrial process heating, advanced innovations, or commercial food services. For more information on the RD&D program, please look at our annual report, which is also available in Spanish. Finally, we want to stay connected with our stakeholders in the research community and the general public. So please visit our website where you can find our annual report, information about our upcoming webinars, and news about the RD&D program. And please reach out to the RD&D team via email with questions, comments, or research suggestions. We also maintain an RD&D page on LinkedIn and on the CEC's research networking platform, Empower Innovation. So just a little background before I hand it over to our speaker today about how SoCalGas is using this technology from Bridger. In 2019, SoCalGas started researching various aerial-based detection technologies with the goal of augmenting our traditional walking survey method. We conducted 3 research phases of pilot studies to evaluate the technology and implementation methodology. We flew 14 diverse flight areas over 28 flight missions, covering more than 4,300 miles of mains and service pipeline and 272,000 customer meters. During these studies, we found that the technology was especially useful at detecting larger leaks, which helps maximize emission reductions while minimizing the impact on operations. And then in 2021, we implemented the technology into our normal operating procedure with our aerial methane mapping program. The aerial methane mapping program is currently successfully detecting and mitigating system emissions at a faster pace than we were with just traditional walking survey. And as you can see on the left-hand side of the screen there, so far to date, we've scanned approximately 40,000 total pipeline miles with the technology, covering about 360,000 feet of pipe per flight hour. And we've detected roughly 1,000 total leaks with the system. That's including both system leaks and customer side leaks. So without further ado, I'd like to introduce our speaker today, the Chief Technology Officer at Bridger Photonics. This is Dr. Mike Thorpe. Dr. Thorpe is the Chief Technology Officer of Bridger Photonics, Inc. He has received his PhD in laser physics from the University of Colorado in 2009, and he specializes in various fields of laser measurement technology, including remote sensing, LiDAR, molecular spectroscopy, and trace gas detection. Mike currently leads the development of Bridger's gas mapping LiDAR and flux curtain technologies for detecting, localizing, and quantifying methane emissions throughout the natural gas value chain. And with that, Mike, lovely introduction. I'm going to hand over presentation to you.
Great, thank you, Eric, for the introduction. And thank you, everybody in attendance, for joining. Excited to share with you what we do with gas mapping LiDAR here at Bridger today. So first off, can everybody see my screen? All right. Well, I'll get started then. Again, thanks for the introduction, Eric. I'm Mike Thorpe, Chief Technology Officer at Bridger Photonics, and today I'm going to be telling you about what we do here at Bridger with gas mapping LiDAR and partnering with SoCalGas to do aerial methane detection and quantification for distribution sector applications. I'm going to go ahead and turn off my camera here while I'm giving the presentation, just for bandwidth purposes. All right. So to start off with just a little bit about Bridger Photonics, who we are and what we do. The company's been around for over 15 years, and we develop advanced laser sensors and analytics to solve industrial challenges. Early on, we were more in precision distance measurement, and we would use that to measure and manufacture and do check on tolerance for complicated parts like this jet engine you see on the left here. More recently, we've been getting into more terrestrial scanning applitions as well as atmospheric gas sensing, and that's given rise to gas mapping LiDAR, which has been a commercial product for Bridger now for about 3 years. So just to step back before I get into talking about the details of how the sensing works and how it performs, just go with the first questions of why we need methane sensing. The bullets on the left here really give kind of the list of usual suspects in terms of the drivers for why methane sensing and monitoring and LiDAR programs are very important. We have the greenhouse gas emissions. Methane is a potent greenhouse gas and also the primary constituent of natural gas. So mitigating these emissions is important for various human activities that emit them. On the right-hand side here, you see a figure I pulled from the EPA carbon emissions inventories for 2020, and you can see the natural gas and petroleum systems are the largest slice of this pie. Now that said, the distribution sector only accounts for about 7% of that slice, and so while still significant, maybe not the primary driver here for some utilities. Important also is public health and safety, as methane presents a fire and explosion hazard, and especially in the urban environment, you have this potential hazard around lots of people and structures and such. And then of course, lost product, and then the integrity management of the distribution infrastructure in order to safely and efficiently deliver natural gas to customers. So this is kind of the high level of why we do it. When we think about how to judge different approaches or technologies that can be used for gas sensing, we like to break it down into key metrics. And there's really 2 main categories here that we think about. There's the first is sensing parameters. So this really comes down to the actionability of the data that is provided by the survey approach coupled with the sensing technology. And then there's deployment parameters, which are more like the economics of the solution, cost per area surveyed, how long it takes to conduct surveys, safety, and then maybe how much emissions you generate versus how much scan you do, or how much emissions you mitigate by finding emissions.
Hey, Mike, not to interrupt you. Sorry to interrupt you, but could you speak a little louder? It's getting a little bit harder to hear you.
Oh, okay, yeah. How is this? Does this sound better?
That's much better. Yes, thank you.
Okay. So I'll just adjust my mic. Okay, and in terms of the actionability parameters, these sensing parameters, got a list of 6 here. The sensitivity, so can the technology detect leaks of a certain size? And importantly, associated with that, Bridger always likes to try to investigate the probability of detection for leaks of a given size. So you kind of know for a given emission rate and maybe environmental conditions such as wind speed, what portion of the leaks of a certain size you can expect to detect. Reliability will kind of encompass not only the ability to sense the leak, but also the ability to see all the areas that you might be interested in finding leaks. So does the survey cover all of the area? Localization, if you get an indication from a survey and a technology type, how close, if you send boots on the ground to go respond, can you send them right there and they don't have to search around to find it? Or is it kind of an approximate location and you have to do more work to pinpoint? Quantification accuracy allows you to compute inventories as you get the rates for all of your leaks, but also prioritize the response to the leaks in terms of fixing them. Persistence is one that is important for remote sensing applications, I think, because when you get a snapshot look that there's a leak, you want to know, is that leak always on, or is it sometimes on and sometimes off? And this informs, if you send boots on, if you're going to actually find something there, or what your chances are of finding something there. And then finally, the attribution, if you can know what infrastructure, equipment, component that the emissions are coming from, you can make more informed decisions on how to respond. So there are a variety of approaches for conducting these surveys, broken them out here in turn into 2 groups. The foot patrol, which is actually sending the boots on the ground to go find the leaks, and then later you get the boots on the ground to go respond to them. And then there's the vehicle patrols, which are more kind of remote techniques where you're surveying from afar and you get indications that there are emissions in certain locations, and then you can send field ops for a ground response sometime after. The foot patrols are really the tried and true, and how it's been done for a long time now. And for distribution application, really these point sensors and the handheld remotes are what's most commonly used for upstream and midstream, more so that the OGI cameras get involved as well. For vehicles, we've got 3 main modes that this will happen with. It's the automobile, and this is typically high sensitivity laser spectrometer, cavity ring down, cavity leak out, tunable diode laser absorption spectroscopy that is mounted on a vehicle, which has air intake to analyze the gas, and then there's anemometers to figure out which way the wind is flowing when elevated emissions or elevated methane concentration is detected, and attempts are made to triangulate back to locations and emission rates. For the airborne piece, we've got a couple of different technology possibilities. There's the LiDAR, which Gas Mapping LiDAR is an example. And then there's imaging spectrometers that use solar radiation and that's reflected off of the Earth and analyzes those signals in order to detect the presence of methane concentration. The difference between that passive approach of the imaging spectrometer or LiDAR is LiDAR actually brings a laser source to illuminate the scene and then analyzes the backscattered laser light that's received by the sensor in order to detect the presence of methane.
Mike, I'm gonna interrupt you again. Your mic. We're getting a few comments that the microphone is intermittently dropping out.
Oh, okay. Shoot. Were we having this problem before the presentation started? Just trying to understand what it could be.
It's kind of towards the end of your sentences, it trails off. Like the beginning of the sentences is very clear, and then towards the end of the sentence, it kind of trails off.
Okay, that's good. Maybe speaking style then. All right, and then so yeah, also satellites. There's been some discussion of using this vehicle approach as well, and these are always imaging spectrometers from there because it's too far of a distance to effectively use laser illumination. All right, this slide, there's quite a bit here, so I'm going to slowly step through it. But this is Bridger's attempt to compile a qualitative representation of sensing approaches for the distribution sector. And what we have here are metric categories that are broken into these sensing and deployment metrics. And I'll step through each one of those to give an idea of what they mean. So sensitivity is referring to the probability of detection for a leak of a given size. And this kind of comprises two components. Is the technology sensitive enough to detect a leak? And is the survey approach being deployed in such a way that that sensor sees all of the areas of interest within the infrastructure, the survey area? Reliability is, again, a component of is all of the area that in the equipment that is of interest being surveyed, and then for the remote techniques, if ground crews are deployed to that location, will they find the leak? Localization is pretty straightforward. Is the technology able to localize to high resolution where the leak is coming from? And quantification, similar thing for each leak. Does the technology get the correct leak rate when sent to measure? For the deployment or the more economic metrics, we have the cost, which is the cost of survey, and in this case, per detected emissions. So you'll see, as you get down to the imaging spectrometer technologies, you get less of the pie filled in here, and that's because they're less sensitive in terms of their detection sensitivity, and so they get, are able to basically detect or find less of the leaks per given cost of the survey deployment. The time to take to conduct the survey is important here. So foot patrols, obviously, you're kind of moving slow. You need to walk around to all the places where there might be leaks, so it takes a long time, whereas a satellite in a very short amount of time can cover a lot of surface area. And then finally, the emissions piece here, we're referring to the detected or mitigated emissions due to the survey compared to the amount of emissions that are generated by deploying that survey. So the approaches that are used to conduct these surveys are listed on the left. And again, we've got the foot patrol, which is the tried and true method. The benefits are that it's highly sensitive. When you find a leak, it's well localized. There are additional tools beyond the point sensors and the remote handhelds that enable quantification of these emission rates when they're found. The downsides really are the labor intensiveness, the time it takes to conduct the survey, and the cost. Moving down, the automobile techniques are kind of a little bit new on the scene, but also have been tried for over a decade now, and they have had some good success with being able to find leaks and do some level of localization and quantification, and also be able to maybe speed up the process because you're driving now instead of walking. But these techniques also have challenges with being able to localize and quantify because these are really inversion problems. You're taking indications from where the leak isn't and trying to invert back or triangulate back to where the emission source is. that was some of the motivation for the aircraft methods, including especially aircraft LiDAR, which Bridger's developed, because this is a downward-looking approach. And so we are in the unique position where we can see all of the surface area, whether it's the distribution pipeline network, but also the customer side stuff, backyards, grills, meter sets. And so it gives us a nice access to see a lot of area that maybe doesn't get seen even in the foot patrol case. And you can see from the first 3 years of commercialization of this technique, we've already got pretty good performance in a lot of these metrics, with maybe sensitivity and quantification being the two that are lagging behind the other metrics. And then if we move to imaging spectrometer, I think the main message here is that the sensitivity of these detection techniques are somewhere between a factor of 15 and 50 poorer than the aircraft LiDAR. And so this leads to a number of, I guess what I'd call deficiencies for the distribution application that almost certainly preclude, at least for the foreseeable future, the effective use of these techniques in distribution. Okay, so now that I've given you kind of the high-level look at methane sensing techniques and why we're doing this, I'm going to shift gears and talk about gas mapping LiDAR specifically. So the approach here is a deployment on small manned aircraft. There are two options for our sensors, helicopter and fixed wing. For the upstream and midstream applications, we always go with fixed wing just because it's better economics. But for the distribution and for some of the midstream applications, we go for helicopter. And for distribution, it's really all about airspace access and just apply the deployment altitude we need and to cover these areas that are highly populated. It's required to have a helicopter. The measurements from the sensor are comprised of two different LiDAR measurements. So a LiDAR range measurement, this is the distance from the sensor to the target on the ground. And the target can be ground, it can be structures, roadways, whatever's down there. We have a LiDAR methane concentration measurement. This measures the path integrated concentration of methane between the sensor and that point on the ground. And then we have aerial photography, temperature and pressure of the environment, and a navigation system that gives us the position and the orientation of the sensor at a high update rate so that we can geo-register the information acquired by the sensor. Then the image on the right shows just how we do the spatial scanning. So we scan in somewhat of a conical pattern so that as the aircraft advances forward, a swath of LiDAR measurement points are captured basically nadir or in the direction below the aircraft. And this allows us to create imagery. So digging into the principles of the gas mapping LiDAR measurement a little more, as I mentioned in the previous slide, we've got the co-aligned LiDAR distance and methane concentration. The distance measurement is done with laser range finding. This is precision and accuracy of the laser range finding that we use is about 0.1 to 0.2 meters, meaning that the distance from the sensor to the ground, if we're flying at 500 feet, is measured to within about a half a foot type accuracy, with even a little bit better precision than that. And then when we couple those distance measurements with the navigation data that gives us the orientation of the aircraft and the sensor, and we're able to determine the direction of the laser measurement at any given point in time, and that allows us with the range to geo-register each LiDAR point on the face of the Earth. So we can make maps that then project onto GIS software and know where all of our measurements are located. The methane concentration LiDAR measurement is performed with wavelength modulation spectroscopy. And so this is a technique that's depicted on the bottom right of the slide, where we park the laser wavelength at the center of methane absorption feature. In this case, it's at 1651 nanometers of the shortwave infrared. And we modulate around that. And that modulation, for every one cycle of the modulation of the wavelength around the center wavelength of that absorption feature, it gives us 2 cycles of the modulation of an intensity of that laser light that is somewhat proportional to the concentration of methane, the path integrated concentration of methane that the laser has passed through. And what's really nice about that is it gives us high accuracy because it's a laser measurement, it's modulated, there's really no signals in nature that mimic this particular signal. So there's low interference from environmental conditions. So we get this highly insensitive measurement to environmental conditions, such as temperature, pressure, ambient light conditions, terrain and infrastructure types, and even precipitation and other conditions like this. Now, we always get the question when people first start thinking about path integrated methane concentration versus a volumetric concentration, about what it really means. There's a graphic on the upper right of this slide that tries to give an intuition for what this measurement provides. Starting on the right, we have an aircraft with this blue and green line going down to the ground, and that represents the LiDAR beam. And we also have a plume depicted in this picture. For A, the beam is going through none of the plume, so there's no concentration of gas that the beam is going through, and therefore the path integrated concentration for this measurement will be 0 ppm here. For instance B, we have 100 meters of the LiDAR beam passing through the plume, and the plume here is listed in pretty small print, but maybe you can see it, listed as 15 parts per million volume concentration throughout the plume. And so what you do to get the path integrated concentration is integrate, or in the case of a uniform concentration plume, you can just multiply the path length times that concentration. So this would be a 1500 parts per million meter measurement. And then in C, we have just one more example where we pass through 30 meters of that 15 ppm plume, and 30 times 15 gives us a 450 ppm meter path integrated concentration measurement. So going from kind of the abstract principles to more practical examples of what this gives us in terms of data, here's some examples of GMO sensor data. So first of all, there's the 3D point cloud. As we're scanning these LiDAR measurements across the terrain and coupling it with the navigation data, we get the point cloud here shown on the upper right of the slide, that this is the 3D topography. So you can kind of see the 3D structures, houses, condominiums, roadways, foliage that describes the structure of the terrain that's being scanned. The middle image gives a representation or an example of plume imagery. So here we have a gas plume kind of near the middle of this image. It's overlaid on Google Earth here, and it's kind of behind the fence line between a house and the freeway here. And this image is derived from taking the 3D point cloud data and converting that, fitting that into a raster image, which we normally think of as a picture. And in this case, we represent the plume as a heat map. So red represents higher concentrations and blue lower concentrations of methane gas. And then everywhere where we're below a certain concentration of methane, we just make it transparent so it's easy to see the satellite imagery or the aerial photography below that plume. The 3D information can be leveraged here in order to determine extra information about that particular plume, like the height of the emission source. Is it coming from on some infrastructure, some structures, or is it coming from ground level? This is really helpful for deploying ground crews to direct them straight to where the emission is coming from. And then, as you may remember from earlier, we get both forward and backward looking measurements of the LiDAR measurements as we scan an area, because we're scanning in this kind of cone pattern. And because of that, we are able to triangulate the height of these plumes and determine the plume height. This is important for applying the correct wind speed, for doing emission rate quantification, and also just for understanding in the vertical dimension where the gas is. And then finally, we have the aerial photography. And this is really nice, snapping images as we fly over, and gives us the contextual information of what the scene looked like at the actual time of measurement, whereas Google Earth gives you what the scene looked like at some time in the past. So the previous slide kind of gave you an idea of what the data and the measurements look like. This slide is meant to convey the performance of the measurements. So Bridger has been conducting a number of blind tests with both customers and academic organizations in order to validate our performance. And most recently, we've done a couple tests with Colorado State University and Stanford University in Midland, Texas, and Ehrenberg, Arizona, in order to test both the detection sensitivity of this technique as well as the quantification accuracy. So the data in the upper right figure shows detection sensitivity test results. And basically what this is we get a controlled release going from a fixed location, and the organization that's conducting the test will release controlled releases of known rate, and will fly over this location repeatedly. And then if the gas mapping LiDAR detects the gas, then we get a 1 on the figure in the upper right. And if it doesn't detect the gas, you get a 0. And importantly here, when we do these tests, we use automated detection algorithms. So we pass the data through the algorithm, and it spits out whether there was a detection there or not. And the parameters for that algorithm are tuned to the same values that we use when we deploy on any job, so that it's not a subjective process or due to bias from human interpretation. It's just the output of what the technology does. So once we have this data, we can apply analysis to it. In this case, what's called a logistic regression has been applied, which can be used to compute the probability of detection for emissions of a given size. And in this case, the x-axis is what's called the wind speed normalized emission rate. So basically the emission rate divided by the wind speed. And then the y-axis is the probability of detection of an emission of that size. And that's given by the blue line, which is the fit result of this logistic regression. The result here is that we get a 0.25 kilogram per hour per meter per second emission rate detection with 90% probability of detection. So for those of you who aren't used to thinking about emissions in kilograms per hour, that corresponds to about 13 standard cubic feet per hour in a 1 meter per second wind speed environment. Now, the deployment conditions here were on a fixed wing Cessna where we were flying a little bit faster. It was at the same altitude that we do our distribution scans, and so it would tend to be just a little bit less sensitive than what we get for a typical distribution deployment. As you'll see in the next slide, in distribution, we tend to fly at 70 miles per hour rather than 100 miles per hour. In terms of the quantification accuracy, these tests were flown at 675 feet, and that we found doesn't affect the quantification, whether we're flying at 500 feet or 675. But the main message here is the emission rate range that we flew for this test was quite large. It was 3 orders of magnitude, spanning from below the detection sensitivity limit of about 0.1 kilograms per hour, all the way up to 1,400 kilograms per hour, really trying to capture the whole detection sensitivity range and all the way up to the biggest leaks that we would expect to see even in the production sector, so that we can understand, as if we make measurements and quantify the emission rate with gas mapping LiDAR, how well can we expect to do? And the results were quite good. over the full range of releases, we were biased in the positive direction by 7.6%, so within 10% of actual. But importantly, especially for the distribution application, for releases of low rate where there's not a large plume to analyze, and here it's represented by releases below 1 kilogram per hour, in the figure on the bottom right, we see that we have a higher positive bias, in this case, 85%. And so basically the takeaway here is that quantifying the smaller releases is more challenging, and for distribution leaks, we can expect to probably get within a factor of 2 at the current state of the technology. So looking at the deployment concept for the distribution sector, again, we deploy on helicopter, either Bell 206 or an MDH 500. We fly at 500 feet above ground level, and at 70 miles per hour is nominal. And with these deployment parameters, we can cover about 12 square miles per day per sensor. And when you think about it, how much, kind of road distance is within that type of area, this is many hundreds of miles, maybe even bordering on 1,000 miles to drive every piece of road within that area. And that can be surveyed in a comfortable day. So you can kind of see the benefit of the ability to fly over and rapidly survey terrain. The survey is portioned out into two different flights. One is the gridded initial flight to get full area coverage, and then we do targeted reflights at detection areas. And this is really to determine persistence. So this helps filtering out detections and doing a better job of sending ground crews only to locations where they need to respond. And then the reporting piece, we do 24-hour reports for large emissions. So, we work with our customers to set a threshold where if it's above a certain concentration, okay, we better respond to this more immediately because it could be a safety hazard. And then the rest of the data comes within 5 business days of the survey completion. Now, importantly here, because we have the LiDAR 3D point cloud data, we are able to do auditable scan area coverage, which we use to track completion of the jobs as they're being flown. We use to make sure we're getting full coverage, and that our customers also can audit and use to make sure that they got full coverage of their surveyed areas. In terms of data products, Gas Mapping LiDAR is operated on a centralized database with a really generalized schema. And what this allows us to do is create flexible relationships between different data types and have unique identifiers for all the different data fields within the database, so that we can scale this up to very large data sets and also be flexible in terms of the types of reports and the views that we create from the data that we collect. So customizable reports can include any of the data that is generated by GML. Common ones are flume imagery, emitter locations, emission rates, persistence, facility infrastructure coverage, and more. And then we can use this data and these views to write reports in a variety of formats, from more simplified reports, spreadsheets, portable documents, just image files, to more sophisticated GIS type deliverables and even database deliverables, which are typically used by our more sophisticated customers to pull into their enterprise data systems. And that allows them to quickly generate workflows within their enterprises for work orders for field crews, emission evaluations and analysis, and ROIs on surveys and stuff like that. So before I wrap up on discussing GML, I want to revisit this distribution sector metrics one more time and highlight 2 categories really. So there's the sensitivity and the quantification of the aircraft techniques. We have identified a lot of low-hanging fruit in terms of the capabilities that we can actually provide with the aircraft LiDAR solution. And Bridger is pushing hard to improve both the sensitivity and quantification. And a lot of this, taking advantage of this low-hanging fruit, is going to be addressed in the release of our second generation gas mapping LiDAR sensor, which is currently being deployed to select customers, and we'll have deployed to all of our customers by the end of 2022. But the basic takeaway here is that as we improve those two categories, you can see that across the board, the aircraft LiDAR is going to become a good performer in almost every category, and will likely be more favorable for distribution application as this happens. So now I'm just going to step back for a moment and look at gas mapping LiDAR from a higher level, where it is and where it's going in terms of the markets that it addresses and where we can apply it. Gas mapping LiDAR is currently deployed over all sectors of the natural gas value chain, from production, transmission, and distribution. And probably right now, production is the largest sector by a lot, but transmission and distribution are probably tied for second, and they're both catching on and growing pretty rapidly. And so with the sensitivity of this technique and the economics of it and the reliability of these measurements, we expect that all sectors will get growth in all these sectors, I guess. Speaking of growth, just to give you an idea of kind of where the company is at with this particular product, we commercialized in 2019, and every year since then, we've had 3 to 4-fold increase in revenue and business associated with gas mapping LiDAR. And we're expecting in 2022 to get same kind of increases. So I think the growth in usage of the technology is a testament to the quality of the product that's delivered here. And that really supports the mission that Bridger Photonics is trying to achieve with gas mapping LiDAR, which is enable clean, safe, and streamlined oil and gas operations by providing actionable data for methane emissions reduction. And with that, that's all I have for today. Thank you so much for your attention. And I'd love to answer some questions if people have them.
Thank you so much, Mike. We do have a couple questions from the chat here that I'm going to throw over to you. So the first question we have is, how does LiDAR differ from hyperspectral imaging, or are they the same basic tech?
No, they are not. Hyperspectral imaging is much more akin to these imaging spectrometers that I was describing earlier in the presentation. Those use ambient light and cameras with filters of some sort in order to get spectral information from the pictures that they're taking. So they rely on passive illumination, whereas the laser illumination, we can do tricks like modulation, where we encode the information in signals that are not found in nature, and that makes us much more insensitive to any environmental conditions. And that's why we're able to achieve such higher sensitivity than the imaging spectrometers.
Thank you. Another question from the chat. What is your typical survey altitude?
Yeah, so for the distribution, typically at 500 feet, and for production, closer to 700 feet.
And then in similar vein, does LiDAR work at night?
It absolutely does. The one thing that doesn't work at night is, or doesn't work as well, is the aerial photography. So we can get our LiDAR measurements anytime we want, because we illuminate the scene with our laser. Now, there are other things to consider, like, are we allowed to fly at night? And that goes into, whether you're operating under visual flight rules or instrument flight restrictions. And then, so it's maybe more of a nuanced conversation, but the fundamental answer is LiDAR can work there.
Thank you. We have actually a couple questions on other gases. So one was, does LiDAR detect propane?
So gas mapping LiDAR does not detect propane currently. Propane can be detected. What kind of the basic thing to think about there is that the color or wavelength that a molecule absorbs at depends on its molecular structure. And so each molecule has what's often referred to as an absorption fingerprint. And if you tune the laser to an absorption feature for a given molecule, then you can perform spectroscopic or LiDAR type measurements on that molecule.
Then in a similar vein, how does the hydrogen blending, future of hydrogen blending, how do you see that impacting sensor ability to properly detect concentrations?
Yeah, so what we usually do there, this is across the supply chain, is if we really want to know the overall leak rate of total gas, then we have to have that fraction of gas that is methane as a value that we can use to scale our measured methane concentration by, to know how much total gas is escaping. As hydrogen is added, there would be less methane, and so we would see just the methane component of that gas. Now down the road, it's possible that if hydrogen becomes more prevalent, we would develop laser technique that would measure hydrogen.
Fantastic. Another one, this is actually a fun one. So if it's not proprietary to share, what are some future technologies that you're researching now?
Yeah, I can share some of them. One that we've been field testing quite a bit is what we call flux curtain. So for measuring and quantifying to high accuracy emissions from larger facilities, whether they're natural gas production facilities or their waste management facilities, mines, etc. And this is a drone technique where we measure the path integrated methane concentration between two drones that are undergoing coordinated flight in the vertical direction. And by measuring the methane concentration as a function of height above ground level and the wind speed at the same time, we can get very high accuracy emissions measurements. We're also actively looking at drone deployment of gas mapping LiDAR. But so far, the economics of manned aircraft deployment and the availability or the lack of restrictions for deploying in that way have dominated over drone deployment of gas mapping LiDAR. So we have not decided to move with the commercial offering for gas mapping LiDAR in the drone space yet.
Thank you. I'm going to actually move to some of the raised hands we have here. So I'm going to pass it over to Tim Rathman. You're unmuted.
Hey guys, can you hear me?
Yes, we can hear you.
Hey Mike, thanks. Great presentation, man. Hey, my question actually was right at your last little new technology space using drones. I'm kind of working with folks. I'm a geologist and working with folks that are in the drone space, and there's a bit of a gap, right? And as you talk about the economics of it's not quite there, but I see the future of sort of smaller projects of methane gas detection as going forward as pretty promising. You do LiDAR, but what about also like a gas detector, like a methane sniffer? Do you have any thoughts on that? Or
we do. A lot of technologies that we compete with will use the sniffer, and and by sniffer, when I think of sniffer, I think of a point sensor that's on a drone, and you kind of have to go everywhere you want to sense the gas in order to get a measurement.
Yeah.
The reason we shy away from that is just the efficiency of making the measurement. Flux curtain is kind of a linear measurement where we measure from one drone to another, and then we vertically sweep that to get a curtain of concentration measurements that we can couple with wind speed to get facility emissions. And then gas mapping LiDAR is kind of a area measurement, right? Because we're scanning areas and looking for plume images. We found that those techniques get us answers and ability to localize, things like this. It is just so powerful how fast you can cover large areas without having to go to each spot you're interested in. And that's why we do it this way. We have made a gas mapping LiDAR sensor. Shoot, it was like 4 years ago now, that mounts on a drone, so you can kind of do smaller facilities in that way. And we haven't commercialized that one just because the manned aircraft deployment, with its ability to cover huge areas so rapidly, it's so powerful that we're focusing on that now. But certainly as we go forward and there's more niches opening up, it's very likely that the drone reemerges and becomes a commercial offering.
Yeah, no, that's awesome. No, thanks for that. And to be honest, I'd like to talk to you further. I'll follow up with you later on, just to kind of continue this discussion. Just because helicopter is pretty expensive with LiDAR, and then there's obviously the economics for it. But I think drones, I've got some insight into other drone companies that I'll send you an email for sure, Mike.
Sounds good. Thanks for the question, Tony.
Yeah.
Thank you, Tim. More questions from the chat here for you, Mike. We got one asking if the technology can detect CO2 as well.
Good question. Our first ever gas mapping LiDAR sensor was a CO2 system. The current version of gas mapping LiDAR is just methane. We do have the potential to make a sensor that does CO2. So far, we kind of haven't found like the silver bullet for that just yet, but if it does exist, we would certainly be interested in discussing it.
And then in a similar vein to that question, would you be able to have two lasers tuned for different molecules scanning at the same time?
This can happen.
Sorry, that was a little hard to hear there, Mike.
Oh yeah, yes, this can be done.
Thank you. Another question we've had, this is an interesting one. One of the audience members says that they've heard that there are pilot shortages. Has that affected the company negatively in any way?
No, we've been finding that we have plenty of pilots to deploy our sensors.
And then another question here regarding flights. So how do clouds or high winds affect Bridger's ability to perform aerial surveys?
Yeah, this is an excellent question. So clouds, all of our pilots currently operate on visual flight rules, which basically means that the ceiling, or kind of the low end of the cloud profile, can't be below, I think it is 1,000 feet above ground level. Now, since this is above the flight altitudes that Bridger uses to deploy, whenever aircraft are allowed to fly under visual flight rules, we can use gas mapping LiDAR. So there's kind of no, anytime we're able to get in the air, we're able to monitor. It is actually a benefit that we fly on the lower side, that even, when it's kind of cloudy up high, we don't find that as an impediment to getting out and surveying. And so we found that, well over 90% of days where we could be out surveying in most geographic areas, we're up flying, which is helpful for deploying the technology. And then can you repeat what was the second half of that, Eric, besides the clouds?
And wind conditions.
Yeah, thank you. And then for the wind conditions, this is often a negotiation between Bridger and the customer regarding detection sensitivity. As the wind blows faster, it sweeps the gas away from the emission source location faster, and we see basically our detection limit is increased. We need bigger release to be able to detect it. And so we usually set up our detection sensitivity and this negotiation with our clients so that anywhere from winds from nothing up to about 25 miles an hour wind speed, we're able to fly. Distribution gets an additional benefit because there's so many structures and foliage in the area where this survey is being conducted that oftentimes the wind speed at the leak location is reduced by all of the topographic features that are blocking the wind.
Thank you. Another question regarding the equipment. How do you calibrate your equipment before each flight?
Yeah, so we have a pretty rigorous QA procedure that each sensor is subjected to before deployment. And then we have a whole list of status measurements and checks we go through before each flight to ensure that not only are all the subsystems working properly, but that the measurement calibration is also still valid before deployment. And then while we're flying, we have ways of cross-checking as well. So we're really concerned about calibration and the accuracy of our measurements, and have lots of analytics in place to ensure that we're getting good performance.
Thank you, and thank you everyone for submitting questions. I have a few more to go through here, but keep them coming, or of course raise your hands, and you can be called on to ask your question. Another follow-up question here, Mike. It's kind of a two-part question. But how do you verify that your emission rate estimate is correct? And what is the confidence interval or uncertainty for your emission rate estimates?
Yeah, I'm actually going to back up to a slide to address that one. Almost all of that verification is just done through controlled release testing, and in particular blind testing, where we don't know the emission rate. We have to measure, submit our answers to whoever's conducting the test, and they compare it against the actuals that they were releasing, as was done in the case of shown on the bottom right here in this slide. And the error bars, so here on the the left-hand axis of this plot is the percent quantification error. So 0 is right on, and then anything off of that is the percent error. And then the x-axis is the release rate. The error bars here are the 95% confidence interval on every measurement as an ensemble. And so you can see that individual measurements can have a good bit of error associated with them. Up at the higher release rates where we're doing well, the 95% confidence interval is anywhere between 40% and 100%. But when you either do multiple passes on the same emission to get multiple looks at a measurement, or you do aggregated emissions from a bunch of different leaks, as you would in emission inventory for a basin or a distribution network, for instance, then you get this averaging effect where you get down to a much smaller error. In this case, over the full range, we were at 7.6% bias error compared to the actual release rates.
Thank you. We actually have a question here in the chat that's more operations based. So I think I can answer it for you, Mike, but the question is, with all the flights taking place, how do you ensure that you're properly staffed to respond and address all of the detections? The way we address that actually is because of all the research phases we've conducted, we have a very good understanding of how many detections we will pick up during a flight through a polygon. And we arrange our flight schedule and polygons such that we do not overload the individual districts when it comes to performing those investigations. and provide 2 weeks notice ahead of time of how many additional investigations we anticipate they will have as a result of the flight occurring. And then I think that's the last current question we have actually in the chat. Do we have any, I don't know if we have any additional questions, please do raise your hand or submit them through the chat. Don't be shy, everybody. We have Dr. Thorpe here available to answer your questions. We got a new one in the chat. So what is the smallest leak that you can detect?
Well, now I feel silly for navigating away from that last slide. Let me get back there. All right. So it all depends on the probability of detection. So here you can see for our 500-foot AGL deployment, we have a non-zero probability of detection all the way down to quite small leaks, maybe even 0.03, 0.04 kilograms per hour, meter per second, where we will still have maybe a 5%-ish, handful of percentage probability of detection. And what that means is, if we fly over 100 of these things, we're going to see 3 or 4 of them. But because there's, in a distribution network, very many leaks of that size, we certainly detect some down there. And so, it's not out of the realm of possibility for us to detect, 1 to 5 SCIF type leaks.
Thank you. I don't see any additional hands raised. Oh, we got a new question popping up in the chat. After detection, can we utilize the gas found once it's captured or redirected? I think that's more of an operational thing. Typically, when it comes to detecting a leak or an emission, that's kind of handled on a case-by-case basis based on the actual investigation, how that is addressed. I have a good question here. Have you detected any false positives through follow-up survey? Yes, I think the chart you have here actually helps answer that as well, Mike, with the probability of detection.
Yeah, and I guess what I would say there is, we have tuned our automated detection algorithm that if it says there's elevated methane there, it's a very high probability that there is elevated methane there. Now, some funny stories. There's been more than once flying over Southern California where we get a detection and we go look at the aerial photography, and it turns out there's a gas plume on the back end of, say, a horse or something like that. And I think from SoCal's perspective, that's probably a false positive, right? We don't want to be finding horse farts because that's not something we'll be responding to. But I would say the technology is very reliable at finding elevated methane. Now, where it's coming from and if it's something we should be responding to, different question altogether.
Yep, absolutely. And I'll also add on to that. The distribution environment is a very interesting environment where you have intermittent releases at times. So there could be a scenario where it's temporal based and you pick something up during the flight, but when you go out for an investigation, the source is no longer there. That's certainly something that occurs.
Yeah, cars are a common culprit for that kind of detection.
Let's see what else we have in the chat here. Can you address the finding of natural seeps, aka field gas? Can you differentiate that from another natural gas system source?
That sounds like one for you, Eric. So you guys have dug into that a little further than we have.
We have. That is something that we're currently investigating. The LiDAR technology itself, I believe, is just picking up methane, and there's no currently, right, Mike? You don't have anything that's picking up ethane to help differentiate it from a natural seep source.
Right. Yeah, and even that would be hard, right? Because those are both heterogenic sources or thermogenic sources of methane. But one thing, that we tend to do is as we get contextual information, like building footprints are a great example. Leaks that are closer to building footprints, we can use that information to help guide, the hazard level for an emission. Same thing with where the seeps are located. If there's no infrastructure around a certain emission and there's a known seep there, that might be enough to guide whether or not a response is issued to that location. So we're big on using contextual information to aid our attribution.
Thank you. There are a lot of questions regarding operational topics, which I could address in the chat, but while we have Mike, Dr. Thorpe here, I'd rather have any questions directed to Bridger specifically, and I can certainly answer your questions about operations in the chat separately. We do have a nice comment here from Paulette saying, not a question, just want to thank you for a great presentation. That's a nice thank you very much, Paulette.
Yeah, thank you.
Any other questions for Dr. Thorpe that the group might have, not so much related to operational practices? While we wait for that, I guess I can take this one easy question. It's how often do LiDAR type surveys need to be performed over a given location to ensure leaks are being detected on a consistent basis? That depends on your system, how frequently you currently survey that section of the system, and how frequently leaks occur in that area. For our program, for our air methane mapping program, we've put a focus on leak-prone pipeline, or pipeline that tends to have a higher frequency of occurrence, because this ends up being a more cost-effective approach for the technology. But that's going to be very specific to your system, and understanding your system is very important for that aspect. All right, we do have a little time left, but we're getting a lot of thank yous in the chat, so it seems to be winding down on questions here. So I will say before people start hopping off here, or see people are hopping off already, thank you so much for coming to our presentation. Thank you, Dr. Thorpe, for sharing Bridger Photonics work with us. It's very exciting. SoCalGas obviously is championing it, and we will give people just a few more seconds here to see if they have any last staggering questions, but yes, thank you.
Yeah, thank you, Eric, for the opportunity. It was fun to present.
And just as a reminder to everyone in the chat that there are handouts available under the handout section of this presentation of GoToWebinar, where you can download these slides that Dr. Thorpe presented today, as well as the RD&D 2021 annual report. Okay. Well, I think I see the attendees are leaving. So thank you, everybody. That'll conclude this webinar. Have a great rest of your Thursday, and we're close to the weekend, so have a great weekend as well.
Thank you.
Thanks, everyone.
Bye.
Bye.